we will proceed with our today's objective. Okay. Okay. Let me share the screen. So yesterday we discussed how to make a spiral coil, right? So for making a spiral coil, direct option is available in our Ansys, right? So we just have to select how many turns we want, the cross section of wire, the diameters of wire, the diameter of wire and the distance between the turns. So there are few parameters that we have to select, but we don't have to draw the spiral structure. It will come automatically, right? So for that, we will go to draw, user defined primitive, segmented helix, then polygon helix. So in polygon helix, yesterday we saw that we get different options, right? We get these options, and I told you what each of that means, right? So I think it is clear for you how to make a spiral coil, both helical structure and planar structure. That I told you yesterday, right? Now, then comes excitation part. So when you are making your spiral coil, so for the excitation, you need some wires coming out of that structure, and that wire should touch your region to give excitation to your coil, right? Yesterday we saw that. So that we have done. We have just take out these wires from our spiral coil structure and have given our excitation through them. But one thing is important, this wire should be long enough that it should touch your region, but it should not be outside of your region, or it should not be less than your region. It should just touch your region, right? For that, I told you that, see, if you have extended your wire in positive X direction, for example, so when you are drawing your region, uh, rather than going for see region, you can draw by two ways, right? It's just a rectangle under inside which your geometry is present, right? So you have two options for that. Either you can just choose this draw box option, or you can choose the create region option, right? Both will serve the same purpose, but we will choose the create region option, especially in spiral type of coil, because uh, then it will be easy for us to make our extended wire touch the region, right? Yesterday I told you this. So see, example, if you have extended your wire in positive X direction at some 200 or so, so what you will do is, while selecting the region, it just so, while selecting the region option, it will ask you percentage offset in each direction. So the direction in which you have extended your wire, just keep that as 0. So what this region option do is, it will start uh, extending the region where your geometry is ending, right? So like here you want your wires to touch your region. So if I want my geometry to touch the region, I'll keep the extension here as 0. They call it as padding. Okay. So here I am keeping it as 0 because I want to touch my extended wires to the region. And then in the rest of the direction, you can give some offset, like here I have given 100 to 100. Just keep in mind that your geometry should be enclosed in it. Okay. And if you are parameterizing any element, example in Z direction, what we have parameterized yesterday, distance between transmitter and receiver, right? So you are parameterizing it. For example, initial value you have kept as 50 mm, right? And then you are parameterizing it from 50 to somewhere around like 200 mm. So while creating the region, you should take into account this point also, that my coil will go, even now it is 50 mm, it will go above till 200 mm, right? So my region should be more than that also. So this point also you should consider, what is the thing that you are parameterizing, not just the initial value, but the final value also, that in any which case your geometry should not exceed your region. Understood? Are you guys understanding what I'm trying to say? Is it clear? Okay, fine. So then yesterday we saw how to give excitation, right? So for giving excitation, what you have to do is just plot visibility. Okay, fine. So this is your okay. This is your geometry, right? Fine. So for giving excitation, select from here. It by default it is on object. So just switch it to phase. Then if this is your coil and this is the input and output terminal, so from one terminal your current should enter. For your transmitter coil, I'm saying. So the below one is your transmitter coil, the above one is your receiver coil. So from one terminal, your current should enter, and from one terminal, it should exit. Exit. Sorry. So from one terminal, it should enter, from other terminal, it should exit. So you have to select the position, select phase, then assign excitation, then current. So while selecting these, keep in mind that if from here, if your current is going outward, so when you will assign excitation to this terminal, just swap the direction. So that it will come out from there, right? And then you can give the value of current here. Okay. See, in wireless power transfer, what you do is you give excitation to your primary coil only, right? And then in the secondary coil, it gets induced, right? By flux linkage, right? Right or no? Okay. So I have just given my excitation to my primary coil. Here I've selected I1. You can parameterize it, or you can just give one single value also, it's fine. And in RX, I have kept it as 0. No need to give current to your receiver coil. Fine. So here excitation is complete. Am I audible to you?
Yes, ma'am.
Yeah, so at least please say yes or no. Okay. That much you can do. Or if you have doubt, you can ask me. Okay.
Okay, ma'am.
And then the next thing is parameters. So in wireless power transfer, you need some inductance, right? So you want to know the inductance of your coil, right? So for that, you have to assign a matrix and select your Rx and TX TX current here. Okay. So if you will not select this, you will not get your inductance for the coil. Okay. So you have to select here both. So yesterday we did this. We have selected this, right? Then mesh operation. Mesh operation is just select the coil and give some value. I told you by default I keep it as 1/4. You can keep at any value you want, or you can keep default also. It's fine. Okay. In some cases you might get error, but most of the cases it works fine. The default value works fine. Okay. Then the third thing is okay setup. You already know how how to get how to set this, right? Here it's fine if you don't set anything. Just in solver, don't forget to set your frequency. Okay, fine. And this option should be checked. It will be checked by default. So it's fine. It is selected by default. So it's fine. You don't have to change anything here. Just in solver, just keep your value of frequency. Yesterday I told you we have kept it as 85 kilohertz because see, you can analyze it for high frequency also. Uh, Mostly I deal with a wireless power transfer application. Sorry, electric vehicle charging application through wireless power transfer. Okay, so there is one standard available for it. We call it J2954. So according to that, your frequency should not exceed like 90 kilohertz. So that's why most of the time I analyze it for 85 kilohertz, but you can keep high frequency also. It's just an analysis part. You are not dealing with any application for now, right? But if you are designing it for a particular application, you should keep like few points in mind that what frequency like standards you should know, right?
Yes,
So in
ma'am.
standards, there are different like parameters that is given. So some of the parameters that like for for me, I need to take care of is for electric vehicle charging application. First is depending on my power rating, uh, range of inductance is given for my coil, right? So that I need to take care of inductance. I need inductance for one more thing. Why I need inductance of my coil for one more thing to check the voltage drop of my coil. See, for making your coil, you will select certain wire, right? Mostly we select leads wire. I'll not go in detail. I'm just telling you. So my wire has some limitations, right? So for insulation limitation, if it is like 2 kilowatt or 2 kilovolts, if it is my uh, insulation limitation. So my voltage drop should not exceed 2 kilovolt, example, right? For that, I should know the inductance of my coil, IXL, right? So for that is also one of the reason why I need inductance of my coil, right? Like self inductance of my coil. Then mutual inductance you anyways need for power calculation, for efficiency calculation, right? your output power will depend how much your flux is linking with the secondary, right? Yes or no?
Yes, ma'am.
Just
Yes, ma'am.
don't even care about the formula. Just don't even care. Like, think in this way. Uh, Whatever will be my output power, it will depend how much flux is getting linked, right? So for that, you need your mutual inductance. So first you need self inductance, then you need mutual inductance. So if you have mutual inductance, if you have self inductance, then coupling coefficient you don't need, right? You can just calculate it. But here, coupling coefficient also we can see. So you don't even need to calculate that. We can see it from here only. Why we need coupling coefficient? Why we need to know our coupling coefficient? Same reason. What is coupling coefficient? Can anyone of you tell me? Can anyone of you tell me what is coupling coefficient? Okay, fine. Uh, your assignment for tomorrow is
Ma'am.
what?
Like,
And are you trying?
coupling coefficient means, yes, ma'am. A coupling coefficient means it's a degree of the system, ma'am.
What? What does that mean? Can you like explain in detail? Okay, fine. So, Bloom coefficient is uh, it is same as your mutual inductance. So how you have self inductance, right? You have mutual inductance. So your coupling coefficient varies from 0 to 1. So it tells you how much the primary coil will uh, induce some mutual inductance. Mutual inductance, sorry, some flux will get induced. So how much that is getting linked to your secondary and how much of it is getting wasted, which we call as leakage flux, that we get to know through our coupling coefficient, right? Right.
Yes,
So if your
ma'am.
coupling coefficient is 1, so coupling between it is very strong. So most of the flux produced by the primary coil is getting linked to your secondary coil, right? And if it is like 0.5, so around not exactly 50%, but some of it, the the flux produced by the primary coil, only some part of it is getting linked to your secondary, rest all is leakage. Okay.
Okay, ma'am.
So that you get to know uh, through your coupling coefficient. So why you need coupling coefficient? Same. If you have mutual inductance, you will get to know your output power. Same, if you have your coupling coefficient, you will get to know your output power. So, see, there is a relationship between mutual inductance and coupling coefficient. It is M equals to K under root of L1, L2. M is your mutual inductance, K is your coupling coefficient, right? And L1, L2 is self inductance of your primary and secondary coil. So now you understand why we need coil simulation, right?
Yes,
And
ma'am.
also, uh, here we will decide some, while designing your hardware, you will decide some dimension for your coil. distance between the turns and all. So, and number of turns. These parameters you will decide to get a particular inductance, right? So when you are deciding these factors, you have to simulate it in some FEA software to see if your assumptions is getting you that same inductance or not. Whatever, like you will do some mathematical calculation and will get these parameters, right? So whatever
Um,
mathematical calculation you have done to validate it, you can go to FEA. Understood? So this whatever I have told you, that on that much things only we will analyze. Uh, First is mutual inductance, second is self inductance, and third is coupling coefficient. Okay. So yesterday I kept it on run. I think it's completed now. Yes, it's done. So let's analyze it. Just go to result. Here, what I have kept as a variable distance between primary and secondary coil, like transmit. When I say primary and secondary, considered it as transmitter and receiver coil. Okay, so you can name it has different names: primary, secondary, transmitter, receiver, right? So if I'll use the alternate words, please, like I don't think you will have any confusion in that, right? Okay, so let's proceed with the analysis. Go to results, right click it, create eddy current. You want it in the form of data table or you want it in the form of rectangular plot, that depends on you. So let's first see in the form of rectangular plot. What is my variable here? Air gap, right? So now we will see how our coupling coefficient is varying with respect to your air gap. Coupling coefficient, we have to see between Tx and Rx, right? So coupling coefficient, you just have to see between Tx and Rx. But in the, okay, uh, let's analyze this first, then I'll tell you that. So this is your coupling coefficient graph. This this is your air gap, and this tells you some memory issues. Some error I got, I think. Okay, fine. So for 50 mm of air gap, my coupling coefficient is around 0. Uh, 0.04, around this. It is too low actually, because this coil is of like smaller dimensions. So the gap I have kept it for. So yesterday when we kept the gap, it is for 25 to around 200, right? So with that much air gap between the transmitter and receiver, our coupling coefficient will be very low. Okay. So today I run it for 15 mm to 50 mm, but I think it is not executed properly. Okay, fine. No, it is not executed properly. So we will just see this, but remember this, that when your coil dimension is too small, just keep the air gap accordingly so that you will get some coupling coefficient. mostly around 0.2 is a good coupling coefficient in wireless power transfer. 0.2, like it should be in wireless power transfer. Actually, for electric vehicle application, see, most of the things I will tell you for electric vehicle application only, because I am dealing with that. So most of the standards that I know, it is for that only. Okay. So these standards and all will change depending on the applications. Okay, so whatever I'll say is not uh, specific to wireless power transfer, but it will be specific to electric vehicle charging application. Okay, fine. And I'll just specify
Fine.
that. Uh, so for electric vehicle charging application, uh, point 0.4 coupling coefficient according to like standards. Point 0.4 coupling coefficient is like the best coupling coefficient that you will get. Okay. So here we are getting it low because we have kept like as per the dimensions, the coupling as per the dimensions, the air gap we have kept uh, too high, right? Higher values we have selected. That's why we are getting such low coupling coefficient. Okay. I tried to rerun it, but I think it is not executed properly, or else I would have shown. Okay, fine. Next thing is next next thing is your inductance. So see, here you will have four inductance, right? So Rx means self-inductance of receiver coil. TX means self-inductance of transmitter coil. And a TX means mutual inductance. So we want all three of it, right? Just so just select all three and new. You'll get to see. So can you see with air gap, your self-inductance is not varying much, right? Only your mutual inductance will vary, right? Understood? Okay. Then, so this, I told you we will analyze this self-inductance, mutual, and then coupling coefficient. So this three analysis you have to do. Then we will see the flux plot. Okay. Can, can you see the flux plot? So So, can you see that the flux produced by your transmitter coil, this flux is getting linked to your receiver coil? Can you see that? Okay, let's try. Now, how we will get this flux field plot? So, first thing what you have to do is you have to select the plane. So, your you want to see flux linkage between transmitter and receiver coil. So select YZ plane. Okay. Then select it. Right click field B, then magnitude of B, then done. Got the plot? right? Now, if you want to see the flux lines, same, select the plane. Here you have to select the plane. It is compulsory to select the plane if you have to see the flux linkage between primary and secondary, right? Right click it, field H. Okay, let's. Can you see flux lines? Can you see? For getting the flux lines, select vector option. Okay. Here also, I think it will work. Field B vector. Are you able to see it?
Yes, ma'am.
Understood? Okay.
Yes, ma'am.
So one thing, let's see from here. See, the flux that is getting linked to your primary coil. So the flux that is being directed, sorry, that is getting linked to your secondary coil is only the useful flux, right? So can you see that the flux produced by the primary coil, which is directed upwards and getting linked to your secondary coil, is only the flux that we are interested in, right? But it has some, uh, like, it will have some flux at below also, below the coil also, right? So that is kind
Yes,
of your
ma'am.
leakage, right? So I don't want to leak, I don't to want this flux to get waste, right? So what I will do is, rather than just keeping, rather than just keeping the coil in the below part, I will place one material that will direct my flux lines only in the upward direction, right? Right? Are you guys understanding this?
Yes, ma'am.
So what I will do is, I will place what properties that material should have if I want it to direct my flux lines. It should be of high permeability, right?
Yes, ma'am.
Then only it will be able to direct my flux lines in the path I want, right? So we will select a high permeability material, usually ferrite we place here also at like at the bottom part of your receiver side and sorry, transmitter side and above your receiver coil. Understood? To direct your flux line in the path you desire, means in the
Yes, ma'am.
upward direction here. In this case, in the upward direction. Okay. So we will place one ferrite plate beneath our transmitter coil and above our receiver coil. Why we need that ferrite plate? You understood? You understood?
Yes, ma'am.
Then
Yes, ma'am.
beneath
To increase the permeability.
of we want to uh, we want our flux lines to directed in upward direction only, right? So we want to give certain path to that flux line. So we need a high permeability material. So ferrite is that high permeability material which we place beneath our transmitter coil and above our receiver coil, right? So after doing this also, to prevent EMI issues in wireless power transfer, a shielding is provided, means a aluminum plate is placed beneath your ferrite plate so that we will the EMI issue is avoided. So EMI issue is like a uh, in especially in wireless power transfer, because we will deal with high power applications, right? Uh, wireless power charging of electric vehicles, sorry, because we are dealing with high power application there, EMI issue arises. So especially in that application, we use aluminum plate beneath our ferrite. Understood? So this is like too much of technical detail. It is
Yes,
not
ma'am.
related to your answers. It is more related to your wireless power charging of electric vehicle. Okay. But I just wanted you to know why we are doing that. Okay. So if we will do that, uh, let me see. I have that simulation, how it will look like. See. So here what I have done is, this is my coil. Can you see these rods? Can you see these rods?
Yes, ma'am.
These rods are of ferrite material. Ferrite material. These rods. See, so I have placed it all over. Why I have see, you can use a plate also instead of this rods, but if you will use rods, you will require less volume of ferrite and it will serve the same purpose. So your coupling coefficient will be somewhat less, but that will not affect that much. Okay, but you will get a great saving in volume of ferrite. Okay, that's why instead of plate, I have placed rods here. Okay, you can keep plate also. Then beneath this, I have placed one aluminum plate in receiver coil beneath and in transmitter coil above, right? So can you see the flux which was getting leak, which was you were getting a flux like flux beneath also, that is not there now. Can you see? Now it is just directed upwards and most of it is getting linked to your
Yes,
receiver
ma'am.
coil. So leakage is less now. Can you see from here? Okay.
Yes, ma'am.
So you understood what this ferrite and aluminum plate do? In mostly in high power application, you should keep this ferrite and
Yes, ma'am.
aluminum plate. For low power application, it's not necessary. But here in high power application, it is necessary. Okay, fine. So we will do this now. I think
Yes, ma'am.
we do it or it's fine. You see, it's like just we are placing ferrite bars and aluminum plate beneath this and deleting this. Okay. Just lose the visibility. So yesterday when we were discussing this, I told you that you can uh, take out these wires from above the coil also and from beneath the coil. But I told you in a wireless charging of electric vehicle, we should take this from above, right? In transmitter coil, because beneath there will come some more material. So beneath this, we will place ferrite, which will touch your coil, and beneath that, you will keep one aluminum plate, which will touch your ferrite, right? That's why you have to position this accordingly. Understood? So for this, for receiver coil, it should be from, so where your ferrite and aluminum is placed in receiver coil, above this coil, right? So if you will
Above.
keep extend your wire
Yes,
from
ma'am.
above the coil, you will not be able to place that correctly, right? So we will change the position of this wire. Okay?
Okay, ma'am.
I've just changed Z position from 5 to -5. Okay? Is it straight? Let me see. This also does not look straight for some reason. Hmm. Yeah, it should be same. This. That's why it was not looking straight. Yeah, it's straight now. Got it? Just do that. Ferrite and aluminum placement. Okay. Select a box. See, I told you we can use ferrite plate also. So in the form of plate also you can make. So how you will make it in the form of plate, I will tell you while we will draw the aluminum thing. Okay. Here I'm telling you in the form of rods that we have just seen, right? Like this rods. Okay. See, this also have some directions and all, like dimensions and all. But for now, because we are just roughly drawing it, we will not consider any dimensions and all. We will take it by our own will. Okay. So we are just assuming it. For now, primary coil, we will just hide it. Sorry. The primary coil, we will just hide it, and we will, secondary coil we will hide, and we will unhide our primary coil. This is your primary, this is secondary. We will deal with one coil, okay? Fine. So then to make rods, select this option. Just draw it anywhere you want for now. Just take care that it should be, the length should be more than your length of the coil. Okay. And draw it from somewhat distance from your center position. So it should be placed on the coil. Okay. Size. X size is this size. It's 30 is fine. Y size is how much? Like why do you want your bar to be? I select 5 and Z side is height of your bar, ferrite bar. Okay. It's fine. Then position. You want it in the center. So your X position will be 0. Right? Your Y position will be minus 2.5. Your Z position will be, it should come beneath this, so -1. Let me see. Think we have to increase the X size because we are not being able to see bottom. Guys are understanding now what I'm doing? So it should be more than this, right? So in X direction, you have to give not, it should not start from 0. You have to give some position. So I'll just give some in positive X direction 2 mm. So it will be 2 mm off center. Off center. Okay. Off center, no, off center. Okay. Understood? You guys understood how I have drawn this block? It is beneath my coil. I'm now you are seeing the bottom view of the coil. That's why you are seeing this. Okay? Understood? Okay.
Yes, ma'am.
So now you want it around your coil, right? So if
Yes,
copy
ma'am.
paste and move, it will not come in circular direction, right? You want it around your this coil, right? So what you will do is you will copy paste it, move it, and then rotate it. Okay, I'll just show you. Copy V. Not copy, sorry. This box. Copy V. Now you got your second box. Just rotate it by 45 degree, right? Understood? So you can change the degree of this. 50. You don't want to, you don't want these blocks to get intersect, right? Maybe 60 is fine. One thing. Yeah. Just rotate it in such a way that it should not intersect. Just keep this in mind. I think it's too wide. That's why it is getting enters. You will just change that. Wait a minute. Hmm. Okay. Let's do it. Copy, paste. Now we are like we have to adjust few things because we are just drawing approximate drawings. We don't have any dimensions and all, right? That's why in this drawing we are just adjusting few things. Okay, But when you have all the dimensions and all, you will not face this issue of adjustment and all, right?
Yes, ma'am.
Z direction 45 to the okay, 50, around 50 is fine. Yes. Now can you see? It's not, oh, it's still intersecting. So this in Ansys, no two geometry should intersect or else it will throw an error here. Okay? Like it should not, it can touch, but it cannot intersect. Okay? It cannot overlap. Okay? Understood?
Okay, ma'am.
Then copy, paste. Again, 45. Okay. Just rotate it. 5. Just do this multiple times. Copy, paste, and rotate. This is just like we did there, right? Copy, paste, and move. Here we are just rotating it. This will not. Still intersecting. The last block we will just delete this because it will not adjust any whatever we will do, it will not adjust in this space. Okay, fine. So this is the way if you want to uh, create see if you want to place your blocks in a circular pattern, or if you want to place means not just for ferrite but for other geometry also, if you want to place anything at some angle, then you will choose this rotate option. Okay, understood?
Yes, ma'am.
So now we will name it as ferrite. Okay, we will assign material ferrite here. Like this. For all the box you have to do the same procedure. Okay, that is for clicking on box 6 while box 4 is getting selected. Huh. Understood this? Now what we need, let's see from top. Can you see? You have placed your ferrite all over the coil. Okay, around your coil. Then the next step is to place your aluminum plate beneath this. So for that, you need a circular aluminum plate for this, right? Because
Yes,
of the
ma'am.
geometry of your coil. So for circular plate, this will give you box, right? For circular plate, you have to choose cylindrical option. Okay. So draw cylinder. Just place it randomly. Anyways, you have to adjust the position. Here, -2. So -1, the diameter of your coil, -1, uh, the width of your ferrite, and then that's why I'm keeping the position as -2 here. So it will come beneath ferrite, right? Right? So radius we will select as what radius we want. Example 40 will be near 30. Mm. Height, I want 2 mm example. Understood this?
Yes, ma'am.
Okay, so front view we will see, then I'll still it is touching your ferrite, right? So adjust your cylinder. -4, I think. No. Oh, your ferrite is touching your coil. That we have not seen, sorry. Oh, so diameter of your coil is 2 mm, right? I'm considering it as one. That's why I have put here -1. So it is like beneath your coil and it should touch your coil, right? So whatever is the diameter of your wire, keep as your Z position. Understood? Okay, everything is done. Yes. Yes, that's right. Okay. So your ferrite is done. And for your aluminum plate, you will select a cylindrical option. So it will ask you what radius you need and what is the position of your plate, circular plate, right? And what is the height you need. So for plate kind of structure, you don't need much height. So I've kept it at 2 mm, right? So radius is, it should be more than this coil. So now I've kept it at 30. I'll just increase it somewhat so that it will be more than my coil. Okay, fine. For now, randomly I'm putting, but these values are not random. When you will design your coil, you will have these values beforehand. So you don't need to worry about that. Okay. Then what is the position? So you want to keep it at, you want the center of your plate to be the center of your Ansys Cartesian system. So I'll keep it at 0 and 0. And for Z position, because you're placing your aluminum plate beneath your ferrite plate, so that's why you have to uh, place it in negative Z direction, right? So how it 4 has come, 2 mm diameter of your wire, then 2 mm width of your ferrite plate. So that accounts for 4 mm. Okay. So beneath this, you are keeping your ferrite plate. Now you can see from here, see, if your model is intersecting anywhere, it will throw this error. Okay. So first part, polygon, helix 1 and box 3 are getting intersect. For box 3, okay, we have not changed this. So now, see now 3D model is validated. That means now no intersection is taking place. So you can check in this way. Okay, understood? So now you understood how to place your ferrite and aluminum. Is
Yes,
it clear?
ma'am. Yes, ma'am.
So in the similar way, you can either duplicate this in your receiver side, or you can follow this. See, if your transmitter and receiver are of same shape and the same dimension, you can just duplicate it. Okay. But if you don't want to draw your receiver again, means just dimension is differing, copy paste that so that you can change the dimensions, right? After copy pasting and moving it to some Z direction above the coil, you can just copy paste, you can just change the dimensions or parameters that you want to change, right? Understood? So here what we will do, this is my receiver coil. Again, drawing all, all of this, like ferrite and aluminum plate, will be tedious, right? So either you can just copy paste this and position it accordingly, or you can just delete this and copy paste the whole coil and then position it. Understood? I'll just copy paste this portion. Model. Hmm. Now you can just give AG to your node. Here, what variable we have kept for air gap? Air gap, okay? I kept it this plus 2 ml so that it will be above your receiver coil. Okay. There are multiple ways to do this. It's not necessary that you follow this way. Whatever you whatever you find easy, just do that. Okay. It should not be two, it should be four. Then you can just copy paste it in all the move options. This is 10. Single step. I think it's fine. Some See, after creating your geometry, some things you might feel like you need to adjust, depending how you are seeing things there. Okay, so just adjust that, because sometimes you predict that it should happen in certain way, right? And your prediction sometimes might go wrong. So that's why just check your geometry from all the views, see if it is like what you have decided it should look. If it is not looking like that, just adjust the parameters that needs to be adjusted. Okay, like I have when I was seeing it from upward, I thought that we need to move it +4, but now when I'm seeing it from front, I got to know that it's just +3. Okay, so like that you can adjust. Understood? Or you can just duplicate this coin. That is all. That will also work. You don't even need to use this copy and move option. I like to do some extra work, I guess. That's why I'm doing all this. Actually, why I prefer this move option is, if I want to change anything in my coil, it is like it comes handy. That's why, like from starting, I use this copy paste and move option. But you can choose, you can do anything is that you feel is like less tedious. Okay, fine. Then now above my coil ferrite is placed. Now aluminum. Oh, +1, 3, +2, 5. Mm, okay. Simulation validate. Nothing is getting touched. Okay. So I've just copy pasted it from here and moved it above, and then adjusted the position in such a way that this ferrite will touch my coil and this aluminum will touch my ferrite. Understood? You can just fully copy paste this coil and you can just duplicate it also. That will also work. Okay, fine. Understood? Let's change the material to aluminum. Okay, so now we have our aluminum, copper, and ferrite. Rest of the things, choose it. So rest of the things are same. You have to give excitation, then select matrix, and everything that we did yesterday, we just have to repeat that. Rx is lost, but why TS is lost? I'm not understanding. Rx is because we changed the position. Okay, fine. We will again give. It's fine. So, region. Excitation is lost. Okay, let's check our model once. Something is not right here. Excitation loss has happened. But I'm not understanding the reason. Okay, fine. We will again give the excitation, okay? Fine. For some reason, excitation has lost, so we will again give it. Just select phase. Okay. First region. Assign excitation. Current. 10 ampere. It is entering from here. So it should leave from the second terminal. 10. Swap direction. Okay. So this is for your TX, right? Inside, this outside, right? Then for your RX, again, same, assign excitation, current, 0 ampere. Assign excitation, current, 0 ampere, swap direction, okay. Fine. Assign matrix. Valid sources. Legal external terminal. An external terminal must border the edge and coincide with the surface of the 3D object. Just doing that. Why it is showing error? Okay, we will create that region again. Zero, 100, 100, 200. The edge of the, it is the edge. I am not understanding why it is throwing error. My lids are touching my edge only, the edge of the region, and still it is showing error. I have to see what is the issue here. Okay, just border the edge of the problem region. That is what is happening. You can see here, right? It is touching my region. Still, it is throwing some error. I have to check what is the issue. This should not have happened. It is touching my region only. Hmm. Okay, we will again try to give similarity. Uh, Excitation, sorry. Whatever error uh, you are getting now, it will get displayed here in message manager. So you can see that where you are facing the issue. Okay. Sometimes it happens that everything you did correctly, it's you feel that you have done everything correctly, still you are getting the error, then you have to debug it. I'm feeling like there is no issue with this, but still it is throwing error. So let's see. Final excitation, current, entry, exit. Here, entry again, then exit. Final excitation, current, hot direction. Okay. The edge of the problem is correct. Yes. Yes. Nothing is wrong here. It is showing error. Can just check this. Why it is throwing error, and I'll tell you tomorrow what was the issue with this. I tried debugging it, but I am not understanding what is the issue because it say that it should like touch the surface of my region, but it is touching the region and still it is showing error. So I'm not understanding what I'm doing wrong for now. Okay. So
Okay, ma'am.
after this excitation, parameter selection, you already know how to do mesh operation, right? So along with copper, you have to do it for aluminum and ferrite as well now. Okay, you have to set
Okay,
your
ma'am.
mesh operation for ferrite and aluminum as well. So just select all the ferrite bars. Both receiver and transmitter. Then assign mesh operation, inside selection, lengthways. You can keep the default value also. It works fine with this. Okay. And then aluminum again, same. Select both. Assign mesh operation, inside selection, lengthways. Okay. So now it for copper, aluminum and ferrite, your mesh analysis is done. In setup, you don't need to change anything. In parameter optometrics also, you don't need to change anything. And then just simulate it. For now, I'm facing some issue with the excitement. That's why this will not work. But you don't have to change anything. Same way you have to give excitation. The mesh operation, you just have to add extra for ferrite and aluminum. Then analysis is same. So now just simulate this, okay? And then compare it with your no ferrite, no aluminum case. So what you will find that your coupling coefficient and your mutual inductance has improved in this case. Okay. So this, I'll run this and will show you the analysis tomorrow. Okay. And I'll
Okay,
also
ma'am.
tell you what is the error I'm getting, why I'm getting this error. Okay, so tomorrow I'll tell you, uh, like I'll show you the comparison as well as we will see why I'm getting this error. Okay,
Okay, ma'am.
fine. So, do you guys have any doubt? Whatever we have discussed today, do you guys have doubt in that?
No, ma'am.
Okay. So
Thank you for the lesson, ma'am.
we will